This video deals with association rule mining. The content is based on data mining, introductory and advanced topics by Margaret H. Dunham. The agenda of this presentation contains introduction, definitions, large item sets, and basic algorithms. Association rules are frequently used by retail stores to assist in marketing, advertising, floor placement, and inventory control. Although they have direct applicability to retail business, they have been used for many other purposes as well, including predicting fault in telecommunication networks. Association rules are used to show the relationship between the data items. And these uncovered relationships are not inherent in the data, as with functional dependencies, and they do not represent any sort of causality or correlation. Instead, association rules detect common usage of items. The grocery store chain keeps a record of weekly transactions, where each transaction represents the item bought during one cash register transaction. The executive of the chain receives a summarized report of the transaction indicating what type of the item purchased have at what quantity. In addition, they periodically request information about what items are commonly purchased together. Here comes association. They find that 100% of the time that peanut butter is purchased, so is bread. That is, bread and peanut butter is purchased together. In addition, 33.3% of the time peanut butter is purchased, jelly is also purchased. That is an association between peanut butter and jelly. However, peanut butter exists in only about 50% of the overall transaction. That is, everybody is not purchasing peanut butter. Those who are purchasing, some people they are purchasing together bread, some people they are purchasing together jelly. Now let us see how is the database. A database in which an association rule is to be found is viewed as a set of tuples where each tuple contains a set of items. For example, a tuple could be peanut butter, bread, jelly, which consists of three items: peanut butter, bread, and jelly. So the transaction here, the transaction one which contains bread, jelly, peanut butter. Transaction two, another customer, he purchased bread and peanut butter. Third customer, he purchased bread, milk, peanut butter. Fourth customer, he purchased beer and bread. And fifth customer, he purchased beer and milk. Let us see what is support. The support of an item or a set of items is the percentage of transaction in which that item occurs. Let us calculate support for few items. First, let us take beer. It appears in how many transactions? The first transaction, it does not contain beer. Second one, it does not. Third one, there is no beer. And the fourth and fifth transactions, they have got beer. Okay. Among five, two transaction has beer. So 2 by 5, it is 40. Similarly, when you go for bread, first, second, third, fourth, among five transactions, four transaction it contain bread. So 4 by 5 into 100. So what is that? It is 80. Similarly, you can calculate support for every item in this transaction table. This is called as a database. Not only for beer, bread, jelly, milk, peanut butter, but you have to go for all combination and you have to see the support for all the items. Here are some definitions. Given a set of items, I equal to I1, I2 up to m number of items. As far as the previous database is concerned, we have bread, jelly, uh, peanut butter, milk, and beer are the 5 items available in this transaction. That is, for simplicity, we assume that only 5 items. Those are bread, jelly, peanut butter, and milk, beer. Okay, only 5 items. And the transaction D, they said T1, T2 up to Tn, n number of transaction, n number of items. But each transaction they may contain from the item set, different set of items. Ti equal to I1, comma I2 up to IIK. So one transaction may contain 2 items, another transaction may contain 3 items, and next transaction may contain 1 or 2, and so on. And IIJ belongs to the item set. An association rule is an implication of the form X implies Y. That means X and Y are purchased together. X வாங்கினா Y வாங்குறோம். X implies Y, where X comma Y is a subset of an item or sets of item called item sets. And X intersection Y is equal to pi, that is nothing. Okay. X comma Y is a subset of I or sets of item called item set, and X intersection Y is equal to pi. For example, bread implies peanut butter in the sense bread and peanut butter, they are in the item set. But bread is different, peanut butter is different. So bread intersection peanut butter equal to null. And the next definition, it is about support. The support we call by the letter S for an association rule. X imply Y is the percentage of transaction in the database that contain X union Y. So this is the support in the sense when I say the association rule, bread implies peanut butter. How many places in the database it is repeated? First one, it contains bread implies peanut butter, and second one, bread implies peanut. That is implies that they are associated together in a transaction. And the third one, bread and peanut butter. Okay, so among 5 transactions, 3 transactions they have got a bread and peanut butter together. So 3 by 5 is the support for the association rule. Bread implies peanut butter. But the confidence, it is represented by the letter alpha for an association rule, is the ratio of the number of transactions that contain X union Y to the number of transactions that contains X. That is, sometimes when you are buying bread, you are not buying peanut butter. Okay. So what are all the places that contain bread? Not you're taking all the transaction, you're taking the transaction that contain. Here X implies Y in the sense X is bread, Y is peanut butter. Okay, so what are all the places X occurs? So first transaction, second transaction, third and fourth. Among 4 transactions in 3 places, bread and peanut butter are purchased together. So 3 by 4. That is the confidence. So that is the difference between support and confidence. Support in the sense you are taking all the transaction into account, and what are all the places X and Y are coming together, that is placed in the numerator. But confidence in the sense what are all the places X is coming and what are all the places X and Y are coming. So that is the ratio we are taking, that is called the confidence, otherwise it is called as a strength, and it is represented by the letter alpha. As we have seen in the previous definition, some of the association rules were taken. Bread and peanut butter, as I said, among the 5 transactions, 3 transactions, it contained bread and peanut butter together. So 3 by 5 into 100. So support is 60%. But when you're going for confidence, I have to take only 4 transactions. That is, what are all the transactions that contains X, that is bread. 4 transactions it contains X bread. So among 4, 3 transaction contains bread and peanut butter together. So 3 by 4, the confidence is 75%. In another one, peanut butter implies bread. What are all the places peanut butter is coming? 1, 2, 3. Okay. So 1, 2, 3, and but when you are calculating support, you have to take into account all the transaction. Among 5, bread and peanut butter are coming together is 3. So 3 by 5 into 100, 60%. But coming for confidence, peanut butter implies bread in the sense you have to look into the transaction where peanut butter are coming. Only 3 places peanut butter is coming. Okay. So all the 3 places bread is also coming. So 3 by 3 into 100, so 100% of confidence. Hope you have understood. So this is how we have to calculate support and confidence. Now you are able to differentiate what is support and what is confidence. Let us come to the association rule problem. Given a set of items I equal to I1, I2 up to IM and a database of transactions D equal to T1, T2 up to Tn, where Ti equal to II1, II2 up to Iik and Iij belongs to I. The association rule problem is to identify all association rules X implies Y with a minimum support and confidence. These values S, alpha are given as an input to the problem. There are so many association rule generation algorithms are existing in the literature. The efficiency of association rule algorithm usually is with respect to the number of scans of the database that are required and the maximum number of item sets that must be counted. The most common approach to finding association rule is to break up the problem into 2 parts. Find large item set as defined in the next slide, and second one, generate rules from frequent item sets. An item set is any subset of the set of all items, that is denoted by I. A large, in other words, we used to say frequent item set, is an item set whose number of occurrences is above a threshold. You can say 5 times, more than 5 times, or more than 3 times, like that. We use the notation capital L to indicate the complete set of large item sets and small l to indicate a specific large item set. The following are the notation being used. D, always it represents the database of transactions as we have used already. Ti, it is a tuple in the transaction, or we can say transaction in the database. S, that represents support. Alpha represents confidence. And X and Y, it represents item sets. X implies Y is an association rule. Capital L, set of large item sets. Small l, large item set in L, that is one of the item set in the large item set. And C, set of all candidate item sets, that we'll see later. And P, number of partitions. And this is a simple algorithm which is used to generate association rules. So here the input is given as database of transactions D, and I is item set items, L large item sets, S is a support, S represents support, and alpha represents confidence. And output will be the association rule satisfying S and alpha. So initially we start with the empty set of rules are for each L which is belonging to capital L, that you all have understood. Capital L represents set of large item set. Small l is one of the large item set from the given item set. Okay. Then for each X belongs to L, that is item set in the sense it may contain more than one item. For example, I could say bread, comma, peanut butter. Bread and peanut butter is one large item set. Okay, that is L, a small l. Then I can say X. X belongs to L. Every item I have to check. X belongs to L in the sense bread belongs to L. That is L here, small l, that represents bread and peanut butter. So I'm taking bread alone such that X is not equal to pi. X is not empty because I said it is bread. Then I have to calculate support of L. What is L? Bread and peanut butter, and divided by support of bread, which is greater than or equal to given confidence. Then I can add the rule like X implies 1 L minus X. X implies அப்படின்னு சொல்லும்போது X அந்த பக்கத்துல இந்த right hand sideல இருந்து remove பண்ணணும். So here it is L. X implies L minus X. And similarly, when I take another one bread, jelly and peanut butter, maybe a large item set, then I have to calculate this for bread, then I have to calculate for jelly, and then I have to calculate for peanut butter. எங்கெங்கெல்லாம் அது கான்ஃபிடன்ஸ் கிவன் கான்ஃபிடன்ஸோடு அதிகமாக இருந்ததோ தென் தட் கேன் பி ஆடட் ஆஸ் அ ரூல். எந்த ஐட்டம் கண்டுபிடிக்கும் போது அந்த மாதிரி இருக்கும்போது அந்த ஐட்டம் இம்ப்ளைஸ் அப்படின்னு போட்டு எல் மைனஸ் எக்ஸ் அந்த ஐட்டம்ல இருந்து இப்போ பிரெட் தான் அதிகமா இருக்குன்னா பிரெட் இம்ப்ளைஸ் பிரெட் வாங்கும்போது ஜெல்லி அண்ட் பீனட் பட்டர் அப்படின்னு we have to form a rule. The a priori algorithm is the most well-known association rule algorithm, and it is used in most commercial products. It uses the property which we call as the large item set property. That is, any subset of a large item set must be large. The large item set also said to be downward closed because if an item satisfies the minimum support requirement, so do all of its subset. Looking at the contrapositive of this, if we know that an item set is small, we need not generate any superset of it as candidate because they all must be small. So here we'll see the lattice to illustrate the concept of this property. In this case, there are 4 items A, B, C, D. The line in the lattice represents subset relationship. So the large item set property says that any set in the path above the item set must be large if the original item set is large. In this figure, the non-empty subset of ACD, it is given here, and it is non-empty subset is given as AC, AD and CD. When you go upward, we will be getting A and also C and D. Finally, A, C, D together, it is coming under this superset. So the basic idea for a priori algorithm is to generate candidate item sets of a particular size and then scan the database to count these to see if they are large. During scan I, candidate of size I, Ci are counted. Only those candidates that are large are used to generate candidate for the next pass. That is, Li are used to generate Ci plus 1. An item set is considered as a candidate only if all of its subset are also large. A priori algorithm. It uses the following property, which we call the large item set property. Any subset of a large item set must be large. When you take here, when you consider this database consisting of 5 transactions, totally only 5 number of items present. So that is taken in the initial level: beer, bread, jelly, milk, and peanut butter. Okay. Consider among these 5, uh, beer, it comes in 2 places, so we have taken as a large item set. And jelly, and jelly is coming in only one place, so that is we have not considered as a large item set. Milk is coming in 2 places, peanut butter is coming, so only we have neglected jelly. And next you are going for combinations. When you take beer, then we combine beer with bread. Beer with jelly is not present in the transaction, so we have not considered. Beer with milk is there, so we have considered. And you can take this, okay? So beer with milk is taken, and beer with peanut butter is there, so that is taken into consideration. All possible combination were taken, and those will be considered as a item sets. The a priori gen algorithm is used to generate candidates of size I. For example, here when you see left side, there are candidates. Using this, you are supposed to find the large item set that is given in the next algorithm. So using, and this is pass number 1, I equal to, sorry, I equal to 1. So using this, you can generate this one using a priori gen algorithm. So Li minus 1 large item sets of size I minus 1. When I take this one as I minus 1, this will be treated as I. The output will be this. When I give input this one, this is the output. Okay. So by combining, finding combination, it generates the next level candidate sets. So these are the input, like in the transaction we have taken into account, for example, it consisting of only 5 items: beer, bread, jelly, milk, and peanut butter. Let us see this one in the next algorithm. Okay, then a priori gen algorithm. First, initially the candidate here we have taken as pi null. For each I belongs to Li minus 1 do. That is for each, in the sense I can consider first beer, then bread, then jelly, then milk, then peanut butter. Okay. So for each I belongs to Li minus 1 do, for each j not equal to I, which is belonging to j Li minus 1. When I take beer, I should not consider beer. Instead, I have to go for bread. Okay. If I minus 2 of the elements in I and j are equal, that is, when I consider beer and bread, no other elements, so I can say when I take these two, remove these two elements, others are same. Okay. Then I can say Ck equal to Ck union I union j. I union j in the sense beer and bread. Okay, so that is coming into this next candidate set, beer and bread. Similarly, I have to go for jelly, and jelly, after applying the next algorithm, jelly will be taken out. Okay, so that is not coming into the account of the second candidate set. This is how they are generating the candidate set. Hope you have understood. And this algorithm is used to generate the large item set. Okay, so I is the item set initially, and using a priori gen, we are going for generating the candidate set. But initially, they are taking into account item sets. And D is the database of transaction. We are very familiar with the transaction about beer, bread, butter, jelly, and peanut butter. And also we need support in order to find whether the item set is large or not. We should know about the support, only then we can analyze and find whether the item set is large or not. The output will be large item set only extracted from the candidate item sets. So a priori algorithm initialize k equal to 0. This is the scan number we are using, and L is equal to pi. Initially large item set is nothing, and C1 is equal to I. That is initially the candidate set. The first time the candidate sets are individual item only. That is beer, bread, jelly, milk, and peanut butter. And you are repeating the process, and we are increasing the scan number as k equal to k plus 1, so that you will be getting 1, and lk equal to lk equal to null for each I belongs to ck do, and we are taking this one as the candidate for each I belongs to ck do. So br, that is belonging to ck, I'm taking this one as a candidate, and ci equal to 0. We are going to see how many times it appears in the transaction, and for each transaction, that is what we have considered T1, T2, T3, T4 and T5 we have seen earlier. For each Tj belongs to database do, for each I belongs to ck do. If I belongs to Cj, then you are increasing the count. Ci equal to Ci plus 1. We are counting how many times it appears. We are incrementing the count. Then you are coming down for each I belongs to ck do. And you are checking after counting how many times it appears in the database. Out of coming out, and you are checking the count is greater than or equal to the support into cardinality of D. Cardinality of D in the sense number of items in the transaction database, number of transactions do. Then lk equal to lk union I. Then you can include this one in the large item set, lk union ii. After that, that will be a large item set that will be added into one of the large item set in the set of all large item set. Okay. Then you are going for generating next candidate set. For that, you should know all possible cases. So you are calling a priori gen of LK using the generated LK large item set in one level, and this is the large item set in one level, and you're calling a priori gen algorithm. Okay, here how they have this algorithm generated this one. How the jelly is taken off, because when you are counting jelly in the transaction in the database, you're getting only one transaction it contains jelly, so which is not treated as a large item set. So we are this algorithm removes jelly. We are getting beer, bread, milk, and peanut butter. Then you are going to generate this one by using a priori gen algorithm. Calling of this one generate this set. Then this algorithm again will eliminate other possible combination because they are not large item set. So it keeps into account only, it keeps only bread and peanut butter as a large item set. Hope you have followed me. Okay. So there are two parts. One is a priori gen, which generate all candidates. This a priori algorithm will find only the large item set by using the transaction, how many times it appears, and counting and finding it. Using, and we have given the threshold as a support, and also using the number of item in the database. Another example is given, that is sample clothing transaction. Here it contains 20 transactions, and you can analyze and find out what support values, confidence, and whatever we have studied you can apply in this transaction and understand in a better manner. And what are all the candidates item set generated, and who are the large item sets, that is also given. Applying this algorithm, and after understanding that particular example and go through this example, you will be understanding in a better manner. Thank you for watching.